Welcome to another video lecture brought to you by FilSciHub Ed, and today we are going to talk about Newton's first law of motion for grade 7 physics. The main purpose of this learning guide is to provide clear definitions and illustration of terms used in physics to describe the law of motion in real-life scenarios. Hi there, my name is Ivy and I am part of FilSciHub Ed, who helped create modules for chemistry, physics, teachers, and students. Let us highlight the roles of few key people whose insight produced major advances. A glimpse of this history can help us appreciate the physical concepts we will be discussing by showing when and how these theories have emerged. It is important, for example, to know whether a theory was just proposed yesterday or have been tried and tested over a long time ago. Not all theories carry equal weight in their acceptance and use by the scientists. Aristotle, Galileo, Newton are the major players in shaping our views of the causes of motion. In his discussion of motion, Aristotle conceived of force, as we have talked about to this point, as a push or pull acting on an object. He believed that force had to act for an object to move, and the velocity of the object was proportional to the strength of the force. A heavy object would fall more quickly to the earth than a lighter object. And because there is a larger force pulling the object to the earth, the strength of this force could be appreciated simply by holding the object in your hand. Aristotle was also aware of the resistance that a medium offers the motion of an object. To challenge Aristotle was equivalent challenging the authority of church and could carry heavy consequences. Galileo was not alone in questioning Aristotle's ideas on motion. Others had noted that drop of objects of similar form but radically different weights fall at virtually at the same rate. Contrary to Aristotle's theory, although Galileo may never have dropped objects from the Leaning Tower of Pisa, he did perform careful experiments with dropped objects and actively publicized his result. In addition to his work of falling objects, Galileo developed new ideas on motion that contradict Aristotle's theory. Galileo argued that the nature tendency of a moving object is to continue moving. No force is required to maintain this motion. Building on the work of others, Galileo also developed a mathematical description of motion that include acceleration. What did Newton accomplish? In addition to his work, Isaac Newton was a successor of Galileo, and he proposed a theory of the causes of motion that could explain the motion of any object. The motion of ordinary objects such as a ball or chair, as well as the motion of heavenly body such as the moon and planets. In Greek tradition, celestial motions were thought of as an entirely different realm from the earthbound motions, thus requiring different explanation. Newton abolished this distinction by explaining both terrestrial and celestial mechanics with one theory. The central ideas in Newton's theory are his three laws of motion and his law of universal gravitation. Newton's theory provided successful explanation of the aspect of motion already known and offered a framework for many new studies in physics and astronomy. And some of this study led to predictions of phenomena not previously observed. Newton's theory in turns have been partially superseded by more sophisticated theories that provide more accurate descriptions of motion. This includes Einstein's theory of relativity as well as the theory of quantum mechanics, both of which arose early in the 20th century. Although the prediction of these theories differs substantially from Newton's theory in realm of the very fast and very small, they differ insignificantly for the motion of ordinary objects traveling at a speed much less than of the light. Newton's theory was a tremendous step forward and still used extensively to analyze motion of ordinary objects. A language not too different from his own, Newton's first law can be stated as an object remains at rest or in a uniform motion in a straight line unless it is compelled to a change by externally imposed force. If it is initially at rest, it will remain at rest. And if it is moving, it will continue to do so with constant velocity. In essence, Newton was reinforcing one Galileo's key ideas of motion in stating the first law. Important postulate of Newton's first law of motion is the concept of balance or equilibrium. An object may experience several forces acting on it, but if these forces balance or cancel out each other, that there is no net force or summation of forces is zero, the object would have a constant velocity and therefore zero acceleration. If the object is initially at rest and there is no net force acting on it, it will remain at rest. And if the object is initially moving and there is no net force acting on it, it will continue moving with the same velocity. Notice that in paraphrasing Newton's first law, we have used the term velocity rather than the term speed. Constant velocity implies that neither the direction nor the magnitude of the velocity changes. When one object is at rest, its velocity is zero, and the value remains zero constant in the absence of external force. If there is no force acting on the object, the acceleration of the object will become zero or will remain zero. The velocity does not change, and if you stop pushing the chair, it stops moving. So this viewpoints problems. However, if we consider a motion of a thrown ball or even a chair moving in a slippery surface, these objects continue to move after the initial push. And Newton made the strong statement that no force is needed to keep the object on moving. And let's consider, for example, the ball rolling on a surface with friction. So the ball's velocity is retarded by the presence of friction. And rolling on a frictionless surface, so no friction opposes the motion of the ball, and the ball velocity is sustained. If we replicate Galileo's experiment and the ramp is not so smooth, the ball will stop before it reaches the height of the initial position. If the ball is made to roll in a horizontal surface, it will eventually stop at some point. But this is because of the presence of the resistive force called friction. So that is also present here on the presentation in a surface with friction. If resistive force is reduced, the ball will roll for a longer distance before coming to stop. If there is no friction at all, we expect the ball's velocity to be sustained as it rolls indefinitely. Here are some examples of the Newton's first law of motion. So as you can see, the ball here, an object at rest, will remain at rest unless affected by unbalanced force. So an object in motion will continue with constant speed and direction unless acted by unbalanced force. Here, this is a book which will not move on its own unless an unbalanced force acts on it. So as you can see here, you have a downward force because the gravity pulls the book and an upward force because the table pushes the book. This is also an example of a Newton's first law of motion. Okay, so for us to know why is this an example, we must take an activity wherein we have to explore the forces at work when pulling against a cart and pushing a refrigerator, crate, or a person. So this simulation can help you in determining whether there is a first law of motion or a second law of motion. And here are some sample learning goals. First is to identify when forces are balanced or unbalanced. Next, is to determine the sum of forces of an object with more than one force on it. Also to predict motion of an object with zero net force and to predict the direction of motion given a combination of forces. This is also a video where you can see basic introduction into Newton's first law of motion, which basically says that an object at rest stays at rest and an object in motion stays in motion unless acted on by a non-zero net force. You can see the video in the link provided on this slide. And to know whether we really understand this learning guide, let us answer some few statements and we must determine whether it is true or false. So the first one, only objects that are stationary or not moving experience zero net force. How about here? Force is always needed to keep an object moving. How about all objects moving at a uniform speed are not accelerating? Next, for an object to sustain its velocity, a constant amount of force must be applied to it. Lastly, a moving object that has an experienced zero acceleration means it has stopped moving. All right, so here I provided an answer where you can review your answer after. And that's it. So these are the references that you could check on. And that's it for today. Thank you so much for listening and watching. And we'll see each other again for the next meeting. And we're going to talk about the second law of motion. Thank you so much.